So here we can start with our topic, properties of the linear prediction error filters. And as we know that the linear prediction filters are having several of the important properties. So one by one I shall be dealing with. So first of all, the demonstration will be for the minimum phase property of the forward prediction error filter. So now, as we have already covered in our previous topics, that the reflection coefficients are basically the correlation coefficients, and the magnitude of the reflection coefficients is always less than or equal to 1 for all the values of the I. So k to the suffix I here we have to use here. So this particular condition and the another relation which we can express as capital E having the power denoted by small f, and to the suffix we have small m, that is equal to the parenthesis holding 1 minus mod square of the reflection coefficient in general k suffix m, and the multiplication to this particular bracket where we have capital E, the suffix is m minus 1 and the power is denoted by small f. So the above condition where the magnitude of the reflection coefficient is always less than or equal to 1, and this new equation, they can be used to show that the zeros of the prediction error filter are either all inside the unit circle or they are all onto the unit circle. So very first of all, we shall discuss if the representation of capital E in general suffix p, if we take the power f, we denote as it is the same notation that we have carried from the previous topics. If it is positive, that means it is greater than 0, so that time whatever the zeros will be there, they will be less than 1 for every ith case here. So here we have the proof by the induction process here, and for p is equal to 1, the system function for the prediction error filter we express here capital A suffix 1 of z, that is equal to 1 added to the reflection coefficient, the first one capital K suffix 1 into z to the power minus 1. So therefore z1 will be equal to minus of the first reflection coefficient capital K1, and capital E to the power we have f, and its first it will be 1 minus mod k1 square. So this difference multiplied by e suffix 0 to the power f, that will be greater than 0 here, what we can take from the second equation on this particular slide here. Now suppose that this particular hypothesis is true for p minus 1, so that time the z suffix I is the root of capital A suffix p of z. So from the previous understandings, here we have the expression capital A suffix p of z suffix I, that is equal to A suffix p minus 1 of z suffix I added by the pth reflection coefficient k suffix p into zi to the power minus 1 multiplied to capital B suffix p minus 1 of z suffix I. So here we can express the RHS of this particular expression as we have A suffix p minus 1 of z suffix I, the first term as it is. The second term here we write the reflection coefficient pth1 capital K suffix p into z to the power, it should be minus p, it should be minus p, and this is in multiplication to the conjugate of capital A suffix p minus 1. So this should be p here, and further we don't have this particular parenthesis here, this is in multiplication to 1 upon z suffix I. So this is equal to 0. So therefore the reciprocal of the pth reflection coefficient that we express as 1 upon capital K suffix p is equal to zi to the power minus p into the conjugate of capital A suffix p minus 1 in multiplication to 1 upon zi, and in the denominator we have capital A suffix p minus 1 of z suffix I. So this ratio is into the negation here, and that is equivalent to capital Q of z suffix I. So here the functional representation on the extreme right hand side that you see, capital Q of Z, is a all pass function. So the generalized all pass function of the form what we have, capital P of Z represented with the pi operation here for the index variable k is equal to 1 to capital N, for the ratio where the numerator is z into zk conjugate added by 1 and in the denominator z plus zk, so for mod zk less than 1. So for this generalized form of the all pass function, the satisfaction to the property is that the magnitude of the LHS that we have representation, mod of Pz will be greater than 1 for mod z less than 1 here. So mod of Pz is equal to 1 for mod z is equal to 1 and mod of P of z less than 1 for mod z greater than 1. So see the changes with respect to the mod z values and mod P of z values. So since the function Q of z is equal to minus P of z divided by z, it follows that mod z suffix I less than 1 if mod Q suffix z Q of z is greater than 1. So here the thing is very clear that since Q of z suffix I is equal to 1 upon the reflection coefficient capital K suffix P and capital E to the power F and in the suffix P is greater than 0. Now in the another case, if the minimum mean square value of the prediction error that can be denoted by capital E to the power we denote small f and to the suffix we denote P minus 1, which is greater than 0, and the value of this minimum mean square error that it is capital E to the power f in the suffix P that is equal to 0. So in this particular case, the magnitude of the reflection coefficient that we represent by mod of Kp is equal to 1 and the magnitude of the function Q of z suffix I is equal to 1. So since this MMSE is 0, the random process that generally we denote by x of n is called as a predictable. So the predictable function is also known to be a deterministic here. So here we are talking about the random process. Okay. Now the specific case of a pure sinusoidal random process if we take, that we can denote with the help of the mathematical expression x of n is equal to the summation k is equal to 1 to capital M for the multiplication of alpha suffix k with the exponential e to the power j of n into w suffix a added by theta suffix k. So here the representation of theta suffix k is nothing but to denote the phases, and these are statistically independent and uniformly distributed over the range 0 to 2 pi. The corresponding autocorrelation representation will be there with the help of the mathematical expression. Here we denote gamma suffix xx of m is equal to the summation for k is equal to 1 to capital M, the multiplication of, here it should be alpha suffix k conjugate, not, it is not the, yes, it should be square, not the conjugate here, and this is in multiplication to e to the power j times m into w suffix k, and the corresponding power density spectrum, here it can be denoted by capital gamma suffix xx as a function of f, that is equal to the summation k is equal to 1 to capital M. Here we have alpha square to the suffix k multiplied to the del of f minus fk, where fk is omega suffix k divided by 2 pi here. So this is the process which is predictable with the predictor of the order. If the order is denoted by small p, it will be always greater than or equal to capital M, as we have the representation from the current formulae. Now, in order to check the validity of all these, let us have the random process to be passed through a prediction error filter which is having the order denoted small p greater than or equal to capital M. So that time the mean square error at the output of this particular filter can be given by, here the representation on the left hand side is somewhat by the Greek letter zeta here, or xi it is, to the power here we have small f in the suffix small p. This is equal to the integral from minus 1 by 2 to plus 1 by 2 over the function here we have represented, which is the power density spectrum denoted by capital gamma suffix xx of f in multiplication to the mod square of capital A suffix p of f into df here. This can further be also expressed as the integration we keep as it is, minus 1 by 2 to plus 1 by 2. At the last we have the representation by df. Here inside this integral we represent the summation that has been taken from the right hand side of the earlier equation for the power density spectrum represented by capital gamma suffix xx of f here. So the summation k is equal to 1 to capital M for the multiplication of alpha suffix k and the alpha is squared multiplied to the del function of f minus fk. Rest of the things are same here. So this is equal to, finally, the summation k is equal to 1 to capital M alpha suffix k alpha is squared multiplied to the mod square of capital A suffix p of f of k here, f suffix k. So here the selection of capital M of the p zeros of the prediction error filter, here it is a forward prediction error filter, to coincide with the frequencies denoted by f suffix k, the minimum mean square error can be forced to the value of 0. Hence we call this to be the minimum phase property of the forward prediction error filter here. So here the thing is very clear that if a random process consists of a mixture of a continuous power spectral density and a discrete spectrum, so that time the prediction error filter must have all its roots inside the units. After completion of this particular first property, let us have the second property with the title maximum phase property of the backward prediction error filter. So here the generalized system function for representation of the backward prediction error filter having the order denoted by small p can be given by the expression where on the left hand side we have capital B suffix p of z, that is equal to z to the power minus p into a conjugate in the suffix p of z to the power minus 1 here. So considering the roots of the function that we have denoted on the left hand side capital B suffix p of z are actually the inverse or the reciprocals of the roots that we have seen for the case of forward prediction error filter, where the system function was denoted by capital A suffix p of z. So thereupon if A suffix p of z is minimum phase, so as we say the roots are reciprocals of the earlier equation. So for the current equation where we have shown capital B suffix p of z, it will be of the maximum phase. So this particular property can also be proved with the same sequence that we have dealt for the earlier case, making the corresponding modifications here. So here if the generalized representation of the random process denoted by x of n, if it is predictable, so that time all the roots of the representation of the expression capital B suffix p of z will lie onto the unit circle. Now after this second property, that it was maximum phase property of the backward prediction error filter, let us have the third property with respect to the linear prediction error filters, which is known by whitening property name here. So suppose here the generalized random process that we denote x of n is of the special type here, the autoregressive. So autoregressive random process can be simply denoted capital AR of P, that is the stationary random process. And let us consider that it is generated by passing the white noise with the variance through all pole filter with the system function given by capital H of Z, that is equal to 1 upon 1 plus summation k is equal to 1 to P, that summation is operated on a suffix k multiplied to z to the power minus k. So that time the prediction error filter having the order denoted by small p will have the system function denoted by the expression of capital A suffix p of z, that is equal to 1 plus the summation k is equal to 1 to p for the multiplication of A suffix p of k into z to the power minus k. So in this expression the predictor coefficients are denoted by A suffix p of k. Simply we can relate it to small a suffix k. Here the response of the prediction error filter will be a white noise sequence that generally we denote W of n here. And for this particular case, the prediction error filter, if we consider, it will whiten the input random process, generally x of n, and therefore this particular filter will be called as a whitening filter, hence the name of the property whitening property. Now let us discuss about the next most important property with respect to the backward prediction error. So this is nothing but the orthogonality of the backward prediction errors here. See, the backward prediction errors generally we have denoted in, I think, the fifth topic by small g suffix m of k. So these backward prediction errors, these are from the different stages into the finite impulse response lattice filter, and these are basically orthogonal here. The orthogonality condition we can also express with the help of the equation capital E of, inside we have g suffix m of n multiplied to the conjugate of g suffix L of n here. So this is supposed to obtain the value 0 for the case small l is greater than or equal to 0 but less than or equal to small m minus 1, and when small l and small m are equal, here it should be small m here, so that time the LHS will hold the value capital E suffix m to the power, we have the representation for the case of backward by small b here. So this property is easily proved just by the substitution of the errors we have denoted g suffix m of n and the corresponding conjugate g suffix L of n, the conjugate here, into the earlier expressions that we have seen here. Now we have capital E of g suffix m of n into the conjugate g suffix L of n here. So here it is equal to the summation k is equal to 0 to m for b suffix m of k multiplied to the summation j is equal to 0 to L for b suffix L conjugate of j here multiplied to capital E of, in the bracket we have x of n minus k multiplied to the conjugate of x of n minus j here. So this can be equal to the summation j is equal to 0 to L for the conjugate of b suffix L of j further multiplied to the summation k is equal to 0 to m bm of k into gamma suffix xx of j minus k here. So gamma suffix xx will be the representation of the autocorrelation sequence here. So in this case the normal equations for the backward linear prediction require the condition that can be denoted by the summation k is equal to 0 to small m bm of k into gamma suffix xx of j minus k to hold the value 0 for j is equal to 1 2 3 and so on up to small m minus 1, and when small j is equal to small m, so that time it will hold the value denoted by capital E suffix m to the power b. So therefore the representation of the earlier equation at the start of this particular property, that it was capital E of, in the bracket we had the multiplication of the backward prediction error G suffix m of n into the conjugate of G suffix L of n. So it will hold the value capital E suffix m to the power b for the backward case, that is equal to capital E suffix m to the power f for the forward case for the condition m is equal to L. This is a typo mistake. Here it should be m is equal to, this should be L here, and this should be the equal to sign here, and it will hold the value 0 for the L, which will be greater than or equal to 0 but less than or equal to m minus 1. So now, after completion of these four major properties with respect to the linear prediction error filters, we have few of the additional properties. So there are basically number of interesting properties we are listing out here for the forward and backward prediction errors into the FIR lattice filter here. So these have been given for the real value data, and here we have one by one the formulation we have provided. Capital E of f suffix m of n into x of n minus I, that will be equal to 0 for I will be greater than or equal to 1 but less than or equal to small m. So in the similar fashion we will have capital E of G suffix m of n into x of n minus I hold the value 0 for I greater than or equal to 0 but less than or equal to m minus 1. We will have capital E of f suffix m of n into x of n, that will be equal to capital E of G suffix m of n into x of n minus m will be equal to capital E suffix m. So in this way we have the next properties which are very simple but important for this particular chapter, linear prediction and optimum linear filters. So here one by one I am showing you all these particular properties, and this will be the last representation here. So here I will conclude this particular topic titled properties of linear prediction error filters.